So a vector subspace, sometimes we just say subspace, say S of a vector space. So say we have some vector space. I'm going to make my things kind of thick here. So a vector subspace of some vector space is a subset of the vector space V. So it's a subset. So that means it's a collection of vectors, because a subset is a set of objects. So it's a set of vectors in V that itself is a vector space. Okay, so let's just do a couple of examples. So examples, just so you can see it, all polynomials, so all polynomials is a subspace of all continuous functions. Okay, so we just did some examples previously. We said that all continuous functions forms a vector space. We also said that all polynomials forms a vector space. But of course, every polynomial is itself a continuous function. So the set of polynomials is a smaller set. If you're a polynomial, you're automatically a continuous function. So I can look at all of the continuous functions, and then I can just pick out some of them. The ones I'll pick out are the polynomials. So that's a subset. And of course, they're both vector spaces, and therefore it is a subspace of all continuous functions. Here's another example. Say, if we consider all vectors of the form, say, x, y, 0 in R3. So I'm describing now a subset of vectors in R3. So R3 is, of course, this is a vector space. And all vectors of this form is obviously a subset. And so we want to see if this subset is also a vector space, but this subset is a vector space. And I won't prove it yet, because I haven't given you the tool to prove it, but we can just sort of, you can go through and check that it's that it's also a vector space. And hence and how would you do that? You just want to check. So if you have something like x, y, 0, so vectors of this form just means that the third coordinate is 0. So if you have another vector like a, b, 0, then what happens if you add them? You get x plus a, you get y plus b, you get 0 plus 0. So that's the right form. You can see that there's a, sorry, that should be a 0. That you can always add, like the negative vector would just be this thing here, which is still of the correct form. And of course that gives you 0, 0, 0, and of course 0, 0, 0 is in the right form, which is great. So it has the 0 vector. Every vector has an additive inverse. You can check that if you scale, if you take a number and you do x, y, 0, then you get nx and y, and of course anything times 0 is still 0, so it's in the correct form. So, and in fact, this is like a copy of R2, so you can visualize this subspace. If you think about R3, if you visualize R3, where this is your first coordinate, that's your second coordinate, that's your third coordinate, then this subspace that I just described would be like the plane on the ground. So it would be like so this is like So this subset is kind of like the ground. It's like the ground or the floor in R3. But the floor itself is just like a copy of the R2. It's like a copy of the two-dimensional plane. And we know that the two-dimensional plane is a vector space because it's R2. And so this is essentially just a copy of R2 sitting inside of R3. Okay, so those are what vector subspaces are, and so let's just do a quick, let's establish a way to identify if a subset is a vector space. Because if you go back to the definition of a vector space, there's a lot you need to check. You have to make sure that the vector addition satisfies all the good properties, you have to make sure you have your scalar multiplication, and you have to make sure they're compatible. That's a lot to check. However, if you have, so if you're taking a subset, that just means a collection of objects from a vector space. So that means you already know that the ambient vector, the ambient space is already a vector space. Then you don't have to check everything. Then you only need to check two things. S is a subspace. That means it is itself a vector space if and only if the following two conditions are satisfied. So instead of going through and checking all of the conditions to be a vector space, you just need to satisfy two conditions. The first condition is if V, and if you take any two vectors that are in the set, then you should be able to add them inside of the ambient vector space. We can add them inside the vector spaces, and we want that thing to be in, if then is in S also. Sorry, I lost my train of thought. Okay, so here you're taking two vectors that are inside of S, but S is a subset of vectors inside an ambient vector space, V, and so that means we can perform vector addition here. This means addition in the ambient vector space V, so we can definitely add them and get a new vector. And the question is that new vector also in S? That's the first condition. And then the second condition is if V is in S, then we want to make sure that RV, or NV, is also in S for every number R or N. I don't know what I wrote. I'll just make that an N, I guess. For every number N. Okay? So again, if you take some vector inside of your set, if you take a vector, so it's inside the set S, and therefore it's a vector inside of the ambient vector space, then we can scale it. So again here, this means scaling in the ambient vector space, so we definitely can't scale it, and the question is, when do we scale it, is it still in the subset? So there are only two things you need to check. Alright? And so now that we have this theorem, we can go back to the previous example. So all vectors of the form xy 0, is that actually a vector space? So I didn't go through the entire check, but now we can just check it using the theorem. So according to the theorem, there are two conditions we have to verify. So this is a verification of the first condition. So if you take something, this is in the form, so this is in the set S, and this is also in the set S. Being in the set S in this example just means that the third coordinate is 0, and if we add them, we get something whose third coordinate is 0. And therefore, if you take two things in this set and you add them, you are still within this set. So that's good. That's condition 1. And over here, if I take something that's in this set, that just means its third coordinate is 0, then whatever the number is, it doesn't matter. This can be arbitrary. When I scale it, I get this, and of course the third coordinate is still 0. So it satisfies conditions 1 and 2. And therefore, it is indeed a subspace.